let's take a look at an example now using this technology and see whether we can make some sense of what we are proposing here. The situation is we had said that we need to identify the elements, and then we are going to use elements like the inertia element, we're going to call it the I element. C element is going to be the compliance element or the spring, and the resistive element or the element that dissipates energy is going to be an R element. The source is a source of effort. So why don't we just put some names in here perhaps? What I can do is we need to put there is a texting here that we use to see here text. So we are going to call this would be the force. I don't know if it will write well here. Force. And then we have in here, this is the wall in here. And then you have the spring in here. Spring. And then we have the damper over here. So we're gonna go and put damper here. And then we have, of course, we also have the mass, don't we? This is the mass. So what we're going to do is we will start the model of this system by recognizing what the velocity of the system are. You have the velocity here for the mass, and you have the velocity for the wall, which is velocity 0. So if I can write or represent rather with a one junction here, you represent with a one junction here, and this would be x dot. Yeah, the velocity. We can say that the source of effort, or this SE element, is attached to it and actually puts power into the system, because this source of effort, we're going to use the two little dots to indicate the value. This is the value F that we know, right? Also, we will put a one junction for the wall in here. What's the velocity of the wall? This is going to be 0. Yeah? Okay. This element that you see here, this one in here, the mass, is going to be connected like this. This is going to be the I element with value m. Yeah, and in here attached to this you have a source of flow, but with value 0 to indicate the wall reference of the wall. So sorry, let me, this is something is not quite right in here, so let me redo this so that this would be fine. What I was saying is that we put the other one junction here to indicate the velocity of the wall. So we do one like this, velocity equals to 0. That's what I was trying to say. For this is for the wall. Yeah. So in here attached to the wall, it makes sense to put the source of rho, source of flow with velocity equals to 0. Yeah. And in between this part in here and this, in between this and the wall are those two elements that see the difference in velocities between the mass and the wall. So to do this, we go x dot minus the velocity of b would be another one junction, which would be x dot minus b. And attached to this, we're going to have the c element, and also you're going to have the r element. Okay? So now we have entered the bone graft model of this system into, in other words, we have created the bone graft model of the system. What remains to be done is actually to enter this into the CAMG software and do the simulation. And that is not too complex. We come into the software in here, and we are going to see how that is done. So you go click over here, then you say Microsoft Office. No, you go directly to the software that would help us do this. And that's the CAMG software right here. So you go in here, anybody knows why I'm getting that this one, this display? So if we have in here this, we should be able to come up with the computer model. In fact, we could make this smaller like that. Yeah. And then we have this all to ourselves the software. And so we're gonna say, okay, go and do new, and what we're gonna do is do the model, do the transcription of that model to here. So in here you go and you put the SE right there, and then you put the one junction over here, and then you have the I element over here. So this goes like this, see? And then we have the zero junction over here like this, and then we also have a 1, so there we go. And then we have to put the C and the R element right there. And then we have yet another one in here, this one right here. And then we have the finally an SF that is in here, and that's also like this. Once you have this picture on the computer, once you have this on the computer, you go to the interface and say MATLAB, and then the two computer programs do some handshake with each other. And we have to wait for a little bit now. And then oh my goodness. And then this will produce the files to do the simulation. I'll do this real quick so that we don't take too much longer. Just I depend on how fast MATLAB is going to come up, because the CAMG software has actually delivered the entire model to MATLAB. And in MATLAB, all we're going to do is to put some of the values of the parameters, and then we will turn in the simulation then. So I'm just hoping that this comes real quick, so we do not delay this much longer. But at this point, the modeling technique that we created is basically over, because we described the system as it's connected, and now it's up to the computer programs to make sure that we have the whole um, files ready to do the simulation. There we go. So MATLAB came up, and then it brings several files that describe that model. We are going to start with a file that is called the model file, and with the model file we'll put just some numbers, and then we'll get a simulation of this. So here's right here for the initial conditions are 0 for both conditions here, 0. And then you have the I element, which is maybe a 2. What did they say? They said 3. Then you have the C element, which is like 1 over 30, which is, these are numbers that produce reasonable plots. And we have the input, which is 10. And then, of course, the other source, which is 0. And then we are going to say do it from 0, and then do it until 5 seconds like that. And that's it. We'll just click on run. And if we do this, lo and behold, we will end up with some results on the simulation. I think there we go. See, produce some plots on the system. We will analyze this in more detail later on, but I just wanted to give you an idea how it works.